Hey everybody, I want to get something out of the way before we get into this senior SMO review problem. We'll call this a function of x, and something kind of troublesome happens here that I think I got resolved. But notice that f of x is equal to 0 over 0, and again that means it's undefined. And you don't notice this until you start using the identities. But this is equal to 0 over 0. That means it's undefined when sin x plus cosine x is equal to 0. And you see that would normally give rise to a vertical asymptote, right? I mean, it's kind of knee-jerk thing. If you have a division by 0 going on in the denominator, often that's a vertical asymptote, at least with rational functions, polynomials. But, and I don't even know when this is equal to 0, but it is. Sin x plus cosine x does cross the x-axis an countably infinite number of times. So this is actually equal to 0 over 0. This expression we're looking at is equal to 0 over 0 when sin x plus cosine x is equal to 0. Now, it's not clear at this point, but notice if we use the right double angle identity for cosine 2x, there's 3 of them. This one in the middle turns out to be favorable because of factoring, okay? But it's very clear that if sin x is equal to minus cosine x, this would be equal to 0, right? So we do have this strange circumstance here, but it turns out we still get a smooth graph because there's really, you have 0 in the numerator also, I guess, is a kind of a naive way of putting it. But anyway, when you do the algebra on this thing, you'll get this statement right here, and we can go ahead with kids' gloves, cancel out, and get that this is equal to root 135 times cosine x minus sin x. Now remember, I didn't even say what it was. We're trying to maximize this expression for all x. So again, the cancellation is okay as long as you're aware of the fact you got to be cautious about when can the denominator be equal to 0. Okay. Now, so again, we're trying to minimize, or excuse me, we're trying to maximize this value, this function f of x. So notice this is a nice time to illustrate Cauchy Schwarz. This is the Cauchy Schwarz inequality right here, folks. CS, Cauchy Schwarz inequality, it's kind of like an inner product here. And you can think of 1 and minus 1 being here. And so you get an inner product, or a dot product is equal to the product of the magnitudes. It's less than or equal to the product of the magnitudes. But notice that this is the well-known trig identity that's always equal to 1. And so what we get right here is cosine x minus sin x is less than or equal to 2. And this is for all x, right? But notice what happens right here. That means that this object right here is less than or equal to the square root of 135 times the square root of 2, right? Again, we just showed that cosine x minus sin x is less than or equal to 2 by the Cauchy Schwarz inequality. And so what is this? This is equal to, this is equal to the square root of 270. Now, I got something fun for you here. I was intrigued by this problem because when I first looked at it, I thought, damn, man, there has to be vertical asymptotes, right? But here is the graph returned by Desmos, okay? Returned by Desmos, and notice how big it gets. This value right here is what? That spot right there is 0, 16, right? And y'all, I'm not talking about the graph itself. I'm just talking about this spot right here, okay? Notice it's 10, 12, 14, 16, 18, 20, right? So that point right there, very close to the maximum value, is 0, 16. But notice that, what do we get? Less than or equal to 270? Less than or equal to 270, but 270 is between 16 and 70, right? That's pretty clear, isn't it? Because 16 squared is 256, right? So we have 270 right here, and then less than 17. And again, I believe this one is 289 when you square it. This one's 256 when you square it. And so this is crystal clear that this happens. And notice how it lines up pretty much with this graph that got returned by technology. Right there, that value. Notice how they put a little hole there. I don't know. I guess that means it's a maximum. But notice this technology. It doesn't really show you there's a lot of holes in this graph. You can't see them, I guess, because of the resolution. But this graph is going to be undefined a countably infinite number of times. But it's smooth. I guess that's what you call removable discontinuities. But in any event, we're done with the problem. And again, this would have fooled me. If I'd have been asked to work this, I'd have been scared stiff about the denominator being divisible by 0. I wouldn't have thought to check the numerator to note that it was 0 also. And again, this is not formal notation. This is what it's equal to when this happens. And so it's undefined anytime sine x plus cosine x is equal to 0. But that doesn't prevent the graph from being, quote, smooth. You just have a bunch of holes in this graph somewhere that, who knows how to figure out when sine x plus cosine x is equal to 0. But in any event, we've finished the problem. The upper bound for this would be it's less than or equal to square root of 270. And I'm not going to go to the trouble it's not advantageous to simplify that any, I don't think. It may be 9's in there, I think. You can take the square root of 9 and get 3, but who cares? So it's equal to this for all x, where the graph is defined, of course. Where the usual caveat, like when you're doing trig identities, prove it's true for all values of theta in the domain of the expression, blah blah blah. But anyway, that's the answer to the question, ladies and gentlemen. I thought it was an interesting problem, and again, this is SMO modification of SMO Senior 2024 review thing. But in any event, good night.